I created a static equilibrium problem that I could not solve using our standard trigonometric methods. And then I solved it using this, and that. Using graphical addition of vectors to solve tough static equilibrium problems without trigonometry. Let's learn physics. Using some strings and spring scales, you can set up things like this in your classroom, actually measure the values of the forces. You know the value of this weight. You can vary your problems and see if they actually work. It's a pretty nice setup and really simple. The problems I set up start with the horizontal string, an angled string, and a weight hanging down. It's not too bad. Then they get more complicated. You can do even angles. So you give the students one tension or just the weight and two angles that you're solving for different things. In all these problems, I have a 100-kilogram concrete block. Different strings, but the weight is always going to be the same. Pulled at an angle of 35 degrees from the vertical by a horizontal rope. Find the tension in the two ropes. Easy way to solve the problem is not set up the equations, but to remember that this is a 1,000 Newton weight. So that's 1,000 newtons, which means that when this is split into its two components, this 1,000 balances that 1,000. And then, using basic trigonometry, sine, cosine, and tangent, you can find that this is 1220, that this side is 700 newtons, and then this tension 1 is 700 newtons. It's not a difficult problem if you speak math. We physics people, we're a bunch of nerds. We love trigonometry, we love mathematics, we speak math, and I've been doing problems this way ever since I was a senior in high school. But what do you do if you're teaching physics first in 9th grade? You can't solve problems like this unless you teach them the math or pretend to teach them the math, because they're just not going to get it. And what do you do if you're teaching students who don't get the math? Why not just eliminate that entire math process and use the protractor and ruler method to solve these problems? This is static equilibrium, so the idea is if you take one vector and you draw the second vector and the third vector using these two, you should get the answer just as nicely as this. I drew the first one I knew. This is 1,000 newtons, so I draw 1,000 newtons, that's 10 centimeters. And I know that this is horizontal. So I'm going to draw the first one, and then draw the second one, and I don't know where this one ends yet. I don't know how long this vector should be, and so I'm just going to draw that of some just long length, indeterminate length. And I know that this is going to go up at 35 degrees from the vertical. It's also going to come down at 35 degrees from the vertical, so I can just draw the line because I know that the triangle is going to close itself. This plus that equals 0. So I draw this, measure 35 degrees from that vertical, and then come down and see where they intersect. 1220 on the trig problem, 700 versus 705. Those are really good answers. Here's number 2. So in this case, strings, 40 degrees, 40 degrees. I can use this method for any angle. This is an any angle method. Split it into two. If this is 1,000 newtons and this is 500 up, that's 500 up, so just deal with one triangle. One side over here, this is 500, and 500 divided by the sine of 40 gives you 778. Good solution, simple solution, but I speak math. Here's the other one. This is pretty sweet. 1,000 newtons straight down. You draw that, you make that 10 centimeters long. And then 40 degrees above the horizontal, you measure 40 degrees above the horizontal with that thing, and then you go up in that direction. I don't know how long that thing is, you just go. Just keep on going. Then this one is going to come up from here in that direction, so I know it's going to meet this at 40 degrees below the horizontal. So I measure 40 degrees, drop that angle, and I get the intersection. Measure this thing, I get 775 and 770. Is it perfect? No. But does it allow you to solve kind of difficult problems with simple tools and get really good answers? Yeah. Here's number 3. This is where the trigonometry gets complicated. Number 3, I'm looking at 20 degrees, 40 degrees, missing T1 and T2. So I know once I find these components, T2 cosine 50, T2 sine 50, T1 sine 70, and T1 cosine 70. Put the actual coefficients in front, and then I know that these two are going to balance each other, and these two are going to balance this one, so I can make two equations. that equation, and then you're going to substitute. So take this one, solve for T1, substitute into this, and solve that. Now, long before I ever get to this, the average student, even in the honors physics class, they're like, I don't know what to do. I have to lead them through this and teach them how to do this thing. But if you're using the other method, you don't have to teach them anything new. It's the exact same problem solution. I know the direction, but I don't know the lengths. Draw first the one you know, 1,000 newtons straight down, you know that, and then pick one or the other. I picked the T1, so I'm going to measure the 20 degrees from the vertical using the protractor, 20 degrees, go up in that direction, indeterminate length, don't know how long it is, and then this one, 40 degrees from the vertical, so 40 degrees from the vertical, that's 40 degrees, and then draw that line, see where they intersect and measure. 735 versus 405. Number 4 is a different one. I'm given the angle and this tension, looking for that tension and that angle. T cosine theta, T sine theta, and do this, and I substitute, and I end up having to take sine over cosine and make that tangent. Honors physics. At least 30% of my students do not know that sine over cosine is tangent. So I have to teach them the new math. But I can solve that exact same problem using this other method in exactly the same way. I know that the weight is 1,000 newtons. I'm going to start with that one every time. And then 1,100 newtons in that direction at 30 degrees, so I just reproduce that. And then draw it. And measure it. Measure the angle. 6.2 degrees. Measure that thing, you get 6.2 degrees. Measure the length of it. Got 550 newtons. It's a pretty good solution. And then finally, this is the one that I couldn't solve, that we couldn't solve using our standard trig methods. I do know the two tensions, but I don't know the two angles. So I have to set up this weird thing where it's 600 newtons cosine beta, 600 sine beta, 1100 cosine theta, two different angles, and 1100 sine theta. And I said these two equal to each other, and the two ups are going to equal the down, so that equals that, and that. Look at a cosine of theta and a cosine of beta, and the sine of theta and the sine of beta, and I don't know how to solve that. I looked up some trigonometric identities, and it's just mathematically difficult. But you know what? This one that I can't solve, I can do it using the other method. Requires a new tool, and this was the thing that took me a while to figure out. So why don't I just use this and use an intersection? This took me back to 7th grade basic math geometry stuff. So you draw the first one, and then I'm going to pick the 600 first. I'm going to take this, measure 600 newtons, and then reproduce that. So I go, there, get that. Now I know that this one is going to come from the other one at 1100 newtons, and then I can take that, measure the 1100, again with this, and go in this direction, get that intersection point. That's the point where it intersects. It's perfect. It also intersects on the other side, but the other side I'm not concerned with. So I take this, I measure, I get 7.5 degrees above the horizontal, 33.5 degrees from the vertical. So how do I check it? This is my check. It's messy, but find 1100, 56.5 degrees, find the two components, 917 and 607. That's 1100 cosine 56.5, 1100 sine 56.5, get those two. And then these two do the exact same process. Now the 595 and the 607, they should be exactly the same, right? They're close. They're really close. But remember, this is a problem I could not solve trigonometrically, and I resorted to using tools to solve it. And spent very little time doing it and got these numbers. Now this should be 1,000, and so the sum of those two should be 1,000. And so I added those two up and I get 995. 995 versus 1,000. That's a 0.5% error. That's really good using simple tools. And then I did the actual angle. So this is the difference is 12. Difference is 12. So 995 and 12. That is 0.7 degrees off from a simple little diagram that is that big. That big. On a tiny little piece of graph paper. It's spectacular. I should have stopped there, but I had to be a math geek and solve some complicated problems in some weird way. So just skip over the next portion to the end and my conclusion. Like I did with the ruler and the protractor, I could draw it like that. So draw the first one, draw the second one, draw the third one, and then use trigonometry to solve the other parts. Here's the second problem, and you get this one I had to use the law of sines, which most of my students don't know. Worked out all right. Here's number 3. Drawn like I would have done it graphically. and then solving it using two different applications of the law of sines, because you can't use sine, cosine, and tangent because this is not a right triangle. And then number 4, came up with this one. I'm looking for this angle and I'm looking for that tension. And law of sines, can't solve that one. Law of cosines, can't solve that one. It's a combination of sine theta, cosine theta, and tension. I couldn't figure out a way to substitute in. I hit a wall, failed on number 4 with this method. And then number 5, I got the real answers. This one actually worked. The law of cosines and the law of sines. Solve this for the angle, and then substitute into that one to get the angle beta of 33.1 degrees. But again, twice, using 2 different trigonometric methods. I failed with number 5 using our standard find the components method, and I failed with number 4 using this method. The great thing about this and this and this is that anybody can do this kind of problem. We don't have to make physics inaccessible to everybody. We don't have to pretend that, oh, you don't have to solve those problems, or you can't solve those problems because you're dumb mathematically. No, we can solve tough problems if we go back to earlier methods that I used early in my career because the book had me use it. And now I use it as a pretty good introduction. But then for honors physics, we want them to actually do this well and the proper way, right? So you want to make physics accessible, real, vector physics accessible? Well, use this, and use this, and use this. Get some graph paper out and solve these problems graphically. For your 9th grade students, or for your students that don't speak math, it's perfect. For the average level students who aren't going to take a college level course that's going to require lots of this, do it this way. It's so good. Thanks for watching Learn Physics. And thanks for that thumbs up too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.